Welcome back to another AP Physics 1 topic overview. In this video, I'm going to be going over friction. So let's get into our facts. Here's the first page of our facts. We have seen these before in the one-dimensional equilibrium video. If you want to go back to that, is in the dynamics playlist. I go over these more in depth. I'm not going to waste your time with them again. Just know that we'll be working with equilibrium a lot. Equilibrium is an object that moves in a straight line at a constant speed, and the forces are going to be balanced. When we make our free body diagrams, it's object on object. That is what a force is, a push or a pull that acts on an object, and is one object on another. They must be in contact besides the force of Earth on the object. So more of our facts that we've done before. Solving equilibrium problems, whenever I say to create a equilibrium equation, this is what I mean. First off, we start off with our free body diagram. If the force is at an angle, we break it into components, which I'll talk about later. And we set up our equations. Up forces equal down forces, left forces equal right forces, what we've done before in the previous equilibrium videos. And the free body diagram is an arrow that represents each force. Each arrow begins on the object and points in the direction in which the force acts. It's always going to be away from the object though. So you're not going to put an arrow going into the object if I'm pushing it. It's just going to be in the direction in which the push is actually acting. Then we have a list of forces indicating the object applying the force and the object experiencing the force. So we'll do this again in the context of the actual examples. I'm not going to show it right now. So more of our facts that we went over before. Mass and weight. We'll see mass again in this and normal force again in this. Again, our equation for weight is Fg equals mg, and g is the gravitational field strength on Earth. That is going to be 10 newtons per kilogram. Your normal force is the force of a surface on an object, so it must be in contact with a surface in order for there to be a normal force. If I'm hanging by a string, I don't have a normal force because I'm not in contact with a surface. Again, mass is how much material I have in an object. Mass doesn't change anywhere I go in the universe. And there on the bottom, platform scale reads normal force, not as important for today. X and Y components. This will be important for one of our examples. So any diagonal force can be written in terms of two perpendicular force components called the X and Y components. When the angle is with the horizontal, the diagonal force, the horizontal component of the force is the magnitude of the force times cosine theta, simply written out as F cosine theta. So whatever number I have at an angle, or it's going to give me a force F, let's say, if I want the horizontal component, it's going to be F cosine theta. Again, this is only if the angle is with the horizontal. If it's with the vertical, it changes, but I'll go over that at a later point. Just want to memorize these ones for now. The vertical component of the force is the magnitude of force times sine theta. Again, just whatever that value is, so they give me whatever force, that's my F. Sine and then theta is the angle that they give me. So we'll see this later on in the video. Alright, so our new facts for today, the friction force. The force of friction is the force of a surface on an object acting along the surface. So very much like the normal force, which is the force of a surface acting upwards on the object or perpendicular to the surface, this force is going to be acting along the surface. So when I annotate my free body diagram, it's going to be pretty much the same thing, the force of the surface on the object. The force of friction acts in the opposite direction of an object's motion. So that's going to be important when we create our free body diagrams. The coefficient of friction, mu, is not a force. So don't make this number, if you have numbers for this, though it doesn't come up often. If you have a number for it, don't put newtons next to it. It's not a force. It is just a number that tells me how sticky two surfaces are. So the only way the coefficient of friction changes is either if I change the surface that I am on, or I change the bottom of the object that is being dragged along that surface. Otherwise, normal force will not change. If I have not changed either of those and I put more mass on top of the object that I'm dragging, the coefficient of friction does not change. It will not change again unless I change the surface that I am on, or I change the bottom of the object that is being dragged across that surface. That's it. There's no other time that the coefficient of friction will change. And the force of friction is equal to the coefficient of friction times the normal force. So we have this here, Ff equals mu Fn. So we get the normal force from equilibrium. We multiply that by coefficient of friction. For the most part, we're going to solve for coefficient of friction in these examples, and for the most part, that's what the AP exam will ask you to do. Sometimes they'll just actually solve for the force of friction in the part 2s, but most of the time they'll make you derive an expression for the coefficient of friction. That's at least what I've seen so far. So let's move into our examples. So example number 1, we have here, you apply a horizontal force of 4 newtons to a block with a mass of 500 grams that allows it to move at a constant speed across a rough table to the right. So with any of these examples, the entire worksheet or problem set is in the description down below, along with the fact sheet. So you can go ahead as much as you like. You can watch the entire explanation. There are chapters in the timelines. You can jump to any part of the examples as you please, or you can follow along with the paper in the description down below. So for part A, we're going to draw a free body diagram of the object. So a free body diagram, again, is just our arrows representing each force, and it's going to be, we're going to annotate this as the object exerting the force on the object at hand. So with this, my first force that I'm always going to have, if last time I checked, if I drop something, it's going to go straight downwards. So that's going to be my Fg. So Fg is always going to be straight down, and Fg is going to be annotated as my force. So again, the object on the object. So the object that is creating this gravity, not the force of gravity, because gravity is not an object, but the force of Earth, because Earth is what is creating gravity. So the force of Earth on the block. We are then going to have this block is on a table, so it's in contact with a surface. So that means I'm going to have a normal force, and that normal force, since there is no angles perpendicular to that surface, is going to be straight up and down. So we're going to have here Fn, and again, when we have Fn, it is the object on the object. Normal is not the object, but the object is the table. So we're going to have here, or the surface, so that is the surface, our table. So we have the force of the table on the block. Then we are pushing this block with a horizontal force of 4 newtons as moving to the right. So that means that the force of push, or the force of the hand, let's say, is going to be to the right. So we're going to put it in this direction. So we're going to call that Fp, let's say, because we're pushing a block. So I'm going to call this Fp. And I'm going to say that is the force of my hand. So force of my hand on the block. Alright, so finally, we are on a rough table. So whenever it says like rough surface, that means I'm going to have some kind of friction, and friction is going to be in the opposite direction of my motion. So since I'm going to the right, my friction is going to be to the left. So I'm going to have this going this way. Let me fix that so it's more straight. I'm going to have my friction going in this direction. And whenever I have friction, it's F subscript F, because F is for friction. So F subscript F, the force of friction. And I'm going to put this over here. So FF. And that is going to be also the force of the table on the block, but that one's the horizontal. So again, just force of table on the block. All right, so that is enough there. We have our free body diagram, and we have our annotations for the free body diagram. All right, so we can move into our next part of the example. So part B, is the block in a state of equilibrium? If so, explain why. So again, whenever we explain something in here to justify something in AP Physics 1, what I like to do is my evidence, reason, and claim. Start off with my fact of physics, explain how that fact applies to the situation, and give my answer, which is the claim here. So, is the block in a state of equilibrium? What is equilibrium? So an object is in equilibrium if it is moving in a straight line at constant speed. This includes an object remaining at rest. That's going to be my evidence here. So it's my evidence for this situation, my fact of physics, because we are moving at a constant speed. If I'm pushing it across the table, I'm in a straight line. So then we can say, since the object is moving in a straight line at constant speed, so that's going to be my reasoning. So since the block is moving in a straight line at a constant speed, we can then make our claim that the block is in equilibrium. So we can say the block is in a state of equilibrium, and that is my claim. It's as simple as that for this explanation. So let's now move into part C. So for part C, if the block is in a state of equilibrium, create your equations of equilibrium. So for this, again, you have your problem solving process for equilibrium problems. Create your free body diagram. We did that already, but let me just remind you of what it looked like. So going straight down, you had Fg. Going to the right, you have here Fp, which is the pushing force on the block. Going up, you have Fn. And to the left, you have FF. All right, so that's my free body diagram here for this situation. All right, so then once we have the free body diagram, we don't have anything at an angle, so we don't have to break it up into components. We set up our two equations. So we're going to have here up forces equal down forces, and then left forces equal right forces. We're going to just focus on up and down for right now. So going upwards, I have the normal force, so Fn, equal to the down force, which is Fg. Then I can break this down further by saying that Fg is equal to mg. So I know now that my normal force is equal to mass times the gravitational field strength. Now I can do my left forces equal my right forces. All right, so my left force here is the force of friction. My right force here is the pushing force. I can further break this down by saying that force of friction, the equation for that is going to be the coefficient of friction mu times Fn is equal to the force in which I push with. And then going one step further, I know Fn is equal to mg, so I can say mu is times mg is equal to the pushing force. All right, so with this, I can now figure out what my part D is, which is actually going to be solving for the coefficient of friction. So you can go one step ahead of me right now if you have the worksheet from the description down below. That's what we're going to do. We're going to solve for mu in just a second. So let's move into part D. I'm going to write this down again in part D, but just the last parts with all the equations all the way out. So we're going to calculate the coefficient of kinetic friction between the block and the table. So again, my equilibrium equations. We have up equals down. Again, it's for forces. I'm just going to abbreviate. So up was Fn. Down was Fg. And we figured out that Fn equals mg. Okay? And then we have the left forces equal the right forces. So left equals right. We had to the left the force of friction. To the right, we had the pushing force on the block. I then further broke this down, mu Fn equals FP, and finally mu mg equals FP. So now I'm going to be asked to solve for the coefficient of kinetic friction. Again, this coefficient of friction is this U looking letter, the Greek letter mu. So if I'm looking at this right now, based on my equilibrium up equals down, I know normal force is equal to the weight of the object because there's no angles. That is multiplied to the coefficient of friction for the force of friction, which is equal to the force in which I push with, because I'm in equilibrium. So what I can do with all of this here, look at this equation here in the middle, mu times mg equals fp. I can solve for mu. So what's attached to mu? Mg by multiplication. So I just do the opposite. I'm going to divide out mg from both sides of the equation. So I should have here my coefficient of friction mu is equal to fp over mg. And it's that simple. If the AP exam was asking you to derive an expression, you'd be done here. You'd plug in what they give you as like the letters. They're going to give you like different variables for the certain forces probably, but that's all you do. This would be the end of it. Since I have some numbers here, and you probably want to do this in a lab just to verify that this stuff works, this is what you'd end up plugging in now. So while I find this coefficient of friction, the force in which I push with was 4 newtons. So I'm going to bring this up here. So we have mu is equal to the force in which I pushed with was 4 newtons. So I'll put this on top. On the bottom, I have the mass. This must be in kilograms. Anything in grams is divided by 1,000. So if I put 500 into my calculator and divide this by 1,000, I'm going to end up with 0.5 kilograms. And then I'm going to multiply this by the gravitational field strength, which is 10 newtons per kilogram. So on the bottom here, kilograms will cancel. I'll be left with just newtons, so newtons over newtons. This shows that my coefficient of friction has no units. So on the bottom, I'm going to have 0.5 times 10. That's going to end up being 5. On top, so let me just show the math here. So I have 4 newtons over 5 newtons on the bottom. So 4 divided by 5 is going to give me 0.8 for my coefficient of friction here. It's a fairly high coefficient of friction. It just depends on the surfaces here in which the block is. Maybe it's a very rough block, maybe it's a very rough table, but that's what we're going to get here, 0.8 based on the math. Again, what you do in a lab is do something similar to this with a constant velocity cart. You'd set it up, you'd end up with your coefficient of friction, and you'd probably test it again to see, to predict what the pulling force would be with a heavier object, most likely. But for this situation, we have a 500 gram block. We're pushing with 4 newtons. It's able to go at a constant velocity. We get this coefficient of friction for this situation. So let's move into our final part of example 1. Alright, so part E, feeling feisty, you stack another 500 gram mass on top of the block. How will this affect the force needed to push the block at a constant speed? Indicate down below, then justify your answer. This is one of those classic quantitative, qualitative questions. We've done some kind of math beforehand. Now we're going to be asked to explain the situation or the equation that we made if this change happened to it. So originally we had 500 grams and we doubled the mass, essentially because we add another 500 grams on top of it. Before I talk about this, with these types of questions, what I recommend you always do is explain it first. Because for the most part with these questions, at least from what I've seen scoring guidelines, it could always change. The scoring guideline, you can't game the system with this. The scoring guideline can change from year to year, and it always will. But for the most part, from what I've seen, is that we use checkoff questions. If you get the checkoff wrong, so if you get the answer completely wrong in the checkoff, they're not going to look at your explanation. For the most part, we'll have in there like note if their explanation or if the check is incorrect, skip it. Because they're grading so many tests over the course of the grading period for the AP exam, they're not going to waste their time if your checkoff is wrong, even if you've written the greatest day in the history of the world. Now, this can change. I've seen it as well where it doesn't matter what your checkoff is for the most part. If you have something in there, it's totally fine. You'll get some points, and that is the goal at the end of the day. But be very careful with this. Do the explanation first, then check off your answer. Same exact thing as evidence, reasoning, claim. I just don't want to claim something and then be married to that claim, essentially. I want to reason myself through it first, then get my claim. It's the same exact idea. If I check off something here, if I'm going to say, oh, it halves, and I'm going to go through everything possible to say that it halves in the explanation. And that's wrong. I'm going to explain that in a second. So let's go through this and get our actual answer. All right, so the equation I'm going to use to drive this was my left equals right here. So we have left equals right from our equilibrium. And my left here, going all the way out, was the force of friction, which we knew was mu mg. And that is equal to the right, which is the force that I push with. Okay? So doing a little bit of a false calculation. Coefficient of friction. The only way this changes is if I change either the surface that I'm on or the bottom of the object that is being dragged across that surface. It doesn't say anything about this besides stacking a mass on top of it. So the bottom of the object is not changing. So that coefficient of friction will not change. That doesn't matter. M in this equation I've created, that's doubling because I have 500 grams originally, add another 500 grams on top. So that means I've doubled my mass. G stays the same. So I should end up having double the force, essentially. So I just have to explain this essentially right then and there, because you can't just do math. I can't just have this equation, then do a rule of ones and say it doubles, because for the most part you have to write out actually what it does. So try your best to explain based on this. You can use this equation in your explanation. Just explain what you've done with this. Don't just do math, okay? You have to be able to explain what you've done, essentially. So with this, I have written out something. It's probably a little bit beyond, a little bit much, but I've tried to explain it to the best of my ability here. So we have here, based on the equilibrium equation I created, the force that I push with, Fp, is equal to the force of friction, Fp equals Ff. Further breaking this down, Ff equals mu Fn. Okay, so I know that Fp equals mu Fn. In this equation, the up force is equal to down forces, or in this situation, the up force is equal to down forces. So Fn equals mg. So when I double the mass, I double the normal force, which will double the force I need to push with, because the coefficient of friction has not changed. This is further justified by the equilibrium equation, Fp equals mu Fn. So again, the only thing I'm doubling here is my mass. That will double the normal force. Double the normal force, the same coefficient of friction, double the force I need to push with. That's it. That's a proper explanation for that. I can check off here double at the top, and that's going to be my answer. That should get me a lot of the points because I've talked about equilibrium, I've talked about the equations that I've created, I've talked about stuff that does not change, and I've talked about the stuff that does change. That's all you have to do for that. Doesn't have to be this nice and pretty. This probably isn't that great at the end of the day anyways, but it doesn't have to be this sciencey. You just, the people that are grading it are not lawyers, they're physicists. They're going to understand what you're saying. When this doubles, this does this. Just talk about equilibrium in this situation. It hasn't changed. It's still in equilibrium, so that's going to be your driving factor, or driving force in your explanation, essentially. All right, so let's move into our next example, fairly similar to the first one. All right, so example number 2. In a lab, you pull a 1 kilogram textbook along the rough ground at a constant speed with a force of 5 newtons to the right. This force is exerted at an angle of 20 degrees with respect to the horizontal. This example is fairly similar to our first example. It is just that we are now working with angles, so we're having to break up stuff into components rather than the first example where everything was just with no angles. So again, I'm going to draw my free body diagram. What I'm going to have here, as usual, going straight down is going to be FG. So I have here FG going straight down, and we know that FG here is the force of the object on the object. So force of Earth on the book. What I also have here, I'm in contact with the ground, so that means I'm going to have a normal force because I'm on a surface. So that normal force is going to be straight up and down. I'll put it annotated there. So Fn is going to be the force of the ground on the book. Again, fairly similar to our first example. Then we are going to pull with a force of 5 newtons to the right at an angle of 20 degrees. That's going to be with a strain. So since anything with a strain, that's usually creating a tension, we call this the force of tension. So I'll call that Ft. And Ft is the force of the strain or the rope on the book. Whatever you want to say, if it's pulling, usually it would be a rope. This situation is kind of big, I guess, but a strain is also fine. So the force of the strain on the book. Then finally, in order to have this, we are on a rough ground. So what I'm going to have here is the force of friction. That is Ff. And that force of friction is going to be as well the force of the ground on the book. So same exact idea as earlier. That's going to be the force of the ground horizontally. So the force of the ground on the book. All right, so there's our free body diagram. Again, fairly similar to the first example. We just have an object that is at an angle. So we have our angled force Ft. All right, so now we're going to move into example part B of example 2. We're going to break up the components here. So with this, we're going to rewrite the forces, but we're not going to write what they are. Again, there's no need to repeat the list of forces. So I'm going to start off with what I have here originally. So I have here Fg. I know I have Ff. And I know I have Fn. Now I have to break up my components into my x or my angled force and then my x and y components. So let's see here. My y component I'm going to call Fty. That's going to be going straight upwards. So that's going to join my Fn. So I'm going to have Fty. And then to the right, I'm going to have Ftx. All right, so for this again, I'm going to use this to create my equilibrium equations if I am in equilibrium. I'm moving at a constant speed. I'll explain this in a second as well. I'm going to use this to do that. And you can see here I have two forces upward. So when I do that, and I'll explain this when we get to it, I don't multiply the forces together, I add them together. So when we do this, it should be Fn plus Fty is going to be equal to Fg, and we'll get to that in part D. So let's just move into part C right now. All right, so for part C, we're just going to explain again, is the book in a state of equilibrium? If so, explain why. So fairly similar to our first example here, what we are going to have. Again, start off with our fact for equilibrium. An object is in equilibrium if it is moving in a straight line at a constant speed. This includes an object remaining at rest. So again, this is our evidence. And if I'm going too fast in the situation, just feel free to pause the video and write down the notes. So again, this is my evidence. Then my reason is my explanation of this fact for this situation. I'm going to say since the book is moving at a constant speed. So that's going to be my reasoning. So since the book is moving in a straight line at a constant speed, my claim can be then that I am in equilibrium. Again, the idea behind this, I start off with the fact. I just don't start off with the book is in equilibrium. I know based on the facts of physics that equilibrium is the answer here. I am in a state of equilibrium. So I can say here the book is in a state of equilibrium. This is due to my facts of physics. That's my claim here. Again, feel free to pause the video to get all of this down because I'm going to move into part D. All right, so part D, if the book is in a state of equilibrium, create your equations of equilibrium. So again, with our problem solving process, we start off with our free body diagram. That was the first part of the question. 1A was if any force acts at an angle, we break it into components. So what I'm going to do is my component diagram. Again, the component diagram is not the original free body diagram, but it will help me create my equilibrium equations here. You do not put components on the original free body diagram. That is very important. It will actually tell you on the AP exam to not do that. If you do components or something that is at an angle, you must just draw it on scratch paper or draw it not on the actual diagram that they give you or the dot that they give you. So for this, I'm going to recreate this. So going straight downwards, I had FG. Going to the left, I have here FF. Going up, I had two forces. I had both FN. And I also have FTY. And to the right, I had FTX. So now, again, we're going to create our two equations. So we're going to have up forces equal down forces. So I'm going to start off with that. And for the rest of this, when I do this, I'm going to abbreviate just up equals down. But up forces equal down forces. So the up forces, when you have two forces in one direction, you just add them together. So I have here going up Fn plus Fty. That is equal to the down force, which is Fg. Okay? Now we're going to break this up further. So I have Fn plus Fty. What does it say for my components here? So my y component, Fty, is just going to be whatever force that I have, so that's Ft, times sine theta. So this is going to be Ft sine theta. Fg, we know Fg is mg. All right, so for right now, we're going to keep this as is. We'll come back to it in a second. That's my up forces, that's my down forces. Now we're going to have my left forces and my right forces. So left forces equal right forces. This one's a little bit more straightforward. Okay, so my left force here is going to be my force of friction. My right force is going to be Ftx. Then I'm going to go one step further. My force of friction, the equation for that is going to be mu Fn. My equation for Ftx, the horizontal component, when I have the angle with respect to the horizontal, it's going to be Ft multiplied by cosine theta. All right, so that's it for right now. I'm going to deal with what Fn is in a second, but these are my equilibrium equations. It's not asking me to solve for the normal force. It's not asking me to solve for the force of friction. I'm going to do that in the next second, in the next part of it, the part E. So let's move into that part right now. All right, so for part E, we're going to solve for the coefficient of kinetic friction between the book and the ground. So for this, we're going to use the equilibrium equations that we created that last part of part D. So I'm not going to go through how I get to this point. If you need to, go in the chapters and go to example 2, part D. But I'm going to show here that up equals down. And for this, my up forces were both the normal force plus the y component of the force of tension, which for this situation is Ft, is the force of tension times sine theta, because my angle is with the horizontal. That is equal to mg, because the downward force, the only downward force, was the force of gravity, the force of Earth, on the object. Then I had left equals right. My left force is equaling my right forces, and my left force was the force of friction. We know that that equation for that is mu Fn, and that's on the equation sheet as well for AP Physics 1. And my right force was Ftx, or the x component of the force of tension. That, when my angle is with the horizontal, is going to be Ft cosine theta. All right, so now it's asking me to solve for my coefficient of friction. So I want to do two things here. Well, I'll solve for mu. So quickly with left equals right, I can do this really easily. Mu times Fn. I have this over here. And I have that mu is equal to Ft cosine theta over the normal force. But we don't know what that normal force is quite yet. I can then go to my up equals down and do a little bit of algebra to get that. So what's attached to my normal force? My y component of the force of tension. So in order to get this away, I'm going to then subtract Ft sine theta from both sides of the equation. And now I should have everything that I need. So Fn is going to equal mg minus Ft sine theta. All right, so now I can plug this one in here. Fn equals mg minus Ft sine theta. I can plug that into this equation. So I'm going to have here mu. Actually, I'm going to move this over here. So I'm going to have here mu is equal to Ft cosine theta all over mg minus Ft sine theta. And again, this is probably going to be as far as they're going to ask you to go for the AP exam. I'm just doing numbers here because everybody loves numbers, and then you can actually test it in a lab. If you, say, have a constant velocity cart, you can do something very similar to this if you have the means of doing it to make sure that the physics actually works, and it will. But this is probably the first they're going to ask you to go, deriving for, say, the coefficient of kinetic friction or the coefficient of friction static if it's like not moving or something like that. So with this now, we're just going to plug in our numbers to get our answer. But this is basically as far as you'd have to go for the AP exam. So let's go the one step further here and get the numbers here if we'd like. So Ft, that is going to be 5 newtons. So I'm going to plug this in here. I'm then going to have cosine of my angle. That is going to be 20 degrees. All over mg. My mass is 1 kilogram. G, I know, is 10 newtons per kilogram. And then minus the same idea here, but for the vertical, I have 5 newtons sine 20 degrees. I'm not going to go through all the algebra here. Just plug in the top into your calculator. Do each one by each step. So 5 cosine of 20, that's going to be around 4.7. On the bottom there, you're going to have 10 newtons minus 5 sine of 20. So plug this in, 10 minus 5 sine of 20. So you should have essentially around 4.7 over around 8.3. Again, for AP Physics 1, the number's not going to be as important. I'm just doing this to show if you had, say, numbers in a lab, this is what you'd plug in these spots here to get the answer. But this is not really important at the end of the day. The actual mu equals Ft cosine theta over mg minus Ft sine theta, that's the most important part here. So I'm going to do this, get my answer here. And my coefficient of friction, if you plugged in all the numbers, you should end up with a coefficient of friction around 0.57. And again, that is with no units. Again, here the most important part here, which I'll square off as well, is my actual derivation, which is mu equals ft cosine theta divided by mg minus ft sine theta. That's the most important part. Okay. For the most part, they will not ask you to plug in numbers on a part 2, and if they do, they're more or less looking for the idea, or at least that was last year when there were any numbers, more or less looking for the actual math that you created versus the actual correct answer. Alright, so now we move into our final part, which is going to be our quantitative, qualitative translation. Alright, so the same exact idea as earlier here with this type of question. This is my quantitative, qualitative translation. So I'm going to use some kind of math that I've done before, and I'm going to try to explain that idea, the equations I've created, and just explain it. So what I'm going to show here on the bottom, the easiest way to go about this, I'm increasing the angle of the strain. So you increase the angle of the strain, but still pull at constant velocity. So that means I'm still going to be in equilibrium, so my equilibrium equations hold. How is the force of friction affected? That's it. So with this, I'm going to just write out my equations here on the bottom that I had here earlier. So I'm going to have here left equals right. I know that my left force was FF, and my right force was FTX. And then going one step further, since I'm only looking for the force of friction and not the normal force or anything like that, I am then just going to say here that FF equals FT, and we know that a horizontal component is going to be cosine theta. That's it. So I can use this here to figure out whether my force of friction is going to increase or decrease. And that's what's called a false calculation, essentially. So since they give us numbers here, I can just plug in the numbers that they've given me and then increase the angle from the angle that they gave me and figure that out. For the most part, they're not going to give you numbers, so you just do a false calculation. With this, what you're probably going to do the best for you is just plug in, say, 1 for my force of tension, or the force that I'm pulling with, and then just change the angle between two different situations. So you'd say the first situation, you can say it's 1 degrees, second situation is 2 degrees, and see what happens when I increase the angle by plugging it into this equation. So again, I'd plug in a number for FT. If they didn't give me 5, I'd plug in some random number. 1's the easiest. I plug in a number for theta. 1's the easiest. And then just increase theta to 2 and see how that changes the horizontal component, which I know is equal to the force of friction based on my equilibrium equations. So then that will show how that affects. So you just have to explain that. You can't just put the math down there. That's not enough. You have to explain it, but you can have equations in the explanation. So if I do this with numbers that they gave me, 5, we have then cosine 20. That's going to give me a value here of around 4.7. So then from this, I'm going to have my other value. I can then make it, say, 5 cosine 30. And just see the difference. I should get a number that is less. So that means my force of friction has decreased. So again, whenever you do this, just make a false calculation. I'm not going to give you numbers for the most part. I've only given you numbers here because this kind of shows you where numbers go in if you're doing a lab on this. But for the most part, they're not going to give you numbers. So if you're asked this type of situation, easiest one, just plug in 1 for the force of tension, plug in 1 for the angle, and then change the stuff that they're asking you to change afterwards to compare it. Since the angle is increasing, I changed the angle. That's good. That's all I have to do to verify what I've done and then explain this. So in my explanation, as you're going to see here, I'm going to talk about equilibrium. So based on the equilibrium equation I created, the component of the force I pull with in the horizontal, Ftx, is equal to the force of friction. So Ftx equals Ff. Further breaking this down, Ft cosine equals Ff. So this is just right equals left, but the same exact idea. When I increase the angle with the horizontal, the value of the horizontal component will decrease. Okay? So this means the force of friction, which is equal to the horizontal component, will also decrease to keep the book in equilibrium. That's it. This all holds true as long as I stay moving in a straight line at a constant velocity. i.e. equilibrium. That's all I have to do for that. Okay, that's the explanation. Again, it doesn't have to be this like detailed with everything. Just try and talk about equilibrium, talk about how the forces have to stay balanced, things like that. The people grading it are not lawyers, they are physicists. They will understand what you're trying to say. Alright, so this is everything for this video here on friction. Again, the fact sheet is in the description down below. The examples are also in the description down below, and this will be in the dynamics playlist, so I'll update that as the year goes on. I hope these examples were helpful, and see you guys in class. Again, here I just want to say, I forgot to check this off. There we go, decrease. So again, hope this was helpful, and see you guys in class.